This lecture I wanted to sort of read it, you to read along with me the original Remsburg book in which I feel things are written very authentically, and instead of just sort of making it into a mathematical or analytical approach, I have also brought along a few samples with me. So, you see here, oh, I think on a white background it shows better. Can you see this? This is a very tiny teeny weeny heat sink. You can see by this. This is also loosely we call the word heat sink. And the other extreme, we have this monster. This I will show against the blue background so that you can see it. You have seen this, absolutely this monstrosity. It is not as if there is some what you call by mistake or somebody wanted to sell things by weight. So, both of them we have here, both of them have their own function. How these have come about is going to be part of this lecture, and for good effect I will also show you these things. Very interesting thing, no? In fact, you can make scrap art with this. Maybe if I show you this fan, now something will fall in place. Can you see? Have you noticed something? If you now keep it in front of it, or in this case, no, let me keep it back of it. The fan has a particular flow pattern, and these fins have been made such that they directly follow the flow pattern. This is slightly different from the chip coolers which I have shown in the earlier pictures, which have radial flow and all that. Seen that? So, if you go back to this fan, you see in the center portion there is not too much of air flow. So, if you are one of the aero modelers, you are even somebody who is a little thing, you must have heard of the word of a spinner. In front of a propeller, usually you have a spinner. That spinner deflects the air, and here we do not need such sort of things for various things about the amount of space. Now, when you put these things together, you will see that these fins are directly in the air flow, and this area and this area has been reserved for components. You can mount power electronic components, and further if you want, you can create manifolds such that the air from there comes here. And not all the semiconductors have a base and they can all be mounted here. But imagine you have other things like sometimes a toroid, which if it is used as a transformer or as a simple what you call inductor, will heat up. So, part of that air, if you have a printed circuit board here, you will have those things all mounted here, so that they also get cooled here. Same thing about some other devices which may need convective cooling. Having said this, I think I will now start with my actual semi theoretical lecture. This has been directly taken from Remsburg book. You may be asking me, why sir, but is it not? Yes, it is true. First thing is I am acknowledging that this is from the textbook. Secondly, you have full access to the textbook. Seen that, no? You have full access to the textbook. Unlike a tutorial class where somebody gives you a little bit of theory and a lot of questions and answers which are likely to come based on the theory. And if you are like some of our what you call good students, you will probably read the theory a little in the beginning, and then after going through all the questions and answers, things will fall in place. Any future question and answer, you have no doubt about it. But the only thing which we have missed is when we took up our education, we did not have this system of coaching classes. Tutorials were there which are very different from coaching classes, and you have to read the original. You have no choice. I am proud that I have read the original. So, I want you to get this book called electronic cooling and have a go at it. So, I thought I will help you with these things. Okay. So, you have this saying introduction and modes of heat transfer and electronic equipment, convection and all this. I have directly, and then I am acknowledging the copyright of CRC Press Limited in 2001. We are approximately 16 years away. So, I am taking the liberty saying, since you are also what do you call knowledge seekers, that you will learn from this book, read the original, and then part of the reading the original is you may need to procure it. Now, allow me to go back to the PowerPoint presentation. So, in case my voice is accented and it is monotonous, you can just lower the voice and read along with me, which I have been telling you all along. See, first of all, electronic devices produce heat as a byproduct of normal operation. I have told you earlier also, an ideal switch in the on condition has no voltage across this, but all the current. The same ideal switch in the off condition will have only voltage across it and no current. So, if you take the product of it, total dissipation is 0. However, a practical switch has both of them. It has in the on condition a small voltage and a large current, and in the off condition a large voltage and a small leakage current. In spite of the best switching transistors, the best switching semiconductor devices, there is a rate of switching also is there, how quickly it turns off and on. That little period required for it leads to heating. When electrical current flows through a semiconductor or a passive device, a portion of the power is dissipated as heat energy. This is real. Besides the damage that excess heat can cause, it also increases the movement in a semiconductor, which cause an increase in signal noise. Since that the noise floor at slightly elevated temperatures keeps rising. Primary focus of this book, and in this case my lectures by which insist that you read the book, is examine in various ways to reduce the temperature of a semiconductor, group of semiconductors. So, you see here, if we do not allow the heat to dissipate, the device junction temperature will exceed the maximum safe operating temperature specified by the manufacturer. For a simplicity's sake, right now I will ignore transient, I will ignore steady state. I will only talk of it as if it is steady state, because transient are slightly different. Transient, because of the dV by dt and d by E by dt, other failures can happen, though you may be in the safe operating area. When a device exceeds the specified temperature, semiconductor performance, life and reliability are reduced. Okay, sir, kindly show this slide. As it is very obvious, failure rate keeps on increasing as the junction temperature increases. So, we have various types of there is logic arrays and dynamic ramps, and then simple thing. This is old, quite old, and probably measured and proven by the mill standard people. Mill handbook 217 gives various things like this. In reality, they keep changing all the time. So, I will go back to the starting point. Nature transfers heat in 3 ways: convection, conduction and radiation. So, if you see all the heat sinks which I have been showing, I will pick on one more heat sink. So, you have seen this, all these fins obviously the way heat is transferred to the ambient is invariably by the most important thing is convection and no radiation. Kindly remember, this is this black color, it looks better on my shirt, is incidental. It has no function in cooling this as compared to this. However, the coating, which is not about the color, the coating, meaning after anodizing and after you do sealing and if you put it and close all the pores and put it, may have some other factors. One of them is it will prevent degradation from the environment. So, to that extent, no, they anodize it and you must seal it. When you seal it, it is convenient if you seal it with some chemicals other than water, which will make which may aid a little in the other properties of it. Okay. So, main thing about a heat sink is not so much about very heavy, not so much about conduction as much it is about convection. So, the what whom I call authority on this starts with, unlike your conventional thing, no, starts with convection. So, we have convection and conduction which need to be radiated. We will explore these in subsequent chapters. As he says, convection is a combination of the bulk transportation and mixing of macroscopic parts of hot and cold fluid elements, heat conduction within the coolant media and energy storage. You have seen that, no, all three are very critical. One of them is transportation, that is where no mass transfer comes into place. So, you have hot and cold fluid elements and from there no all the things which you have, which is part of fluid mechanics, saying how well a boundary layer is formed, how you have what do you call turbulent flow and how heat is exchanged within the media comes under study. In the initial part of this lecture, I have said, oh, everything is reduced to analytical. A good theory avoids unnecessary experimentation, which is what the, I mean, please look it up, though I have the reference here, I want you to look it up. A good theory avoids unnecessary experimentation and probably speed to market. So, even if a thing like a, what do you call, mobile phone, if somebody does quick small calculations, we can make use of all the what you call things, and finally you may have to end up with only one single prototype and next is a production or pilot run is possible, if you understand the analytical portion of it, and the analytical portion is used in simulation, and simulation is based on physical verification upfront. In that case, well, I will not withdraw my comment in the earlier thing, everything has its place. I hope you agree with me. Now, come back to my what do you call this slide. Convection can be due to the expansion of the coolant media in contact with the device. This is called free convection or natural convection. So, what happens here is buoyancy is set up. The moment something expands, that the density comes down and immediately it will try to rise up. This is the basis of natural convection, which is good. My body gets what do you call naturally convected like yours, and if you are one of those people who check weather, there are two more important parameters they keep defining other than the temperature and humidity. There are things like real feel and feels like, both of them real feel and feels like. Take the case of ambient conditions of the skin, understand, no? And clothing what we wear. So, with light clothing and proper ambient things, sometimes the if it is cold outside, it feels chillier than outside, which is the wind chill factor. Understand, no? Light clothes and there is a wind blowing at the same temperature, you have a wind chill factor and feels colder. If ambient is maybe let us say 10 degrees, it may feel like 3 or 4 degrees lower. At the other end of it, if you are clothed well and already the ambient is a little high, especially if it is above 27 or 28, the moment you cover yourself, it feels much hotter. And the places where we live, when the ambient temperature shows around 35, 36, real feel may hit 40 and 42. It feels hot. Those winds which come about may or may not cool, they may be heating. So, we have this issue of two things called natural convection and forced convection. In the case of natural convection, the expansion is the one that aids it. But then by definition, we have a little problem, not problem, the reality of natural convection is orientation of the fins is critical. It should be in the same direction in which the things are, the fluid is flowing. Maybe in the next picture, I will show you a picture of a printing head which moves in a printer. You will notice that that solenoid mechanism again dissipates heat and fins there are kept horizontally. So, as the printing head moves, especially if it is a dot matrix printer, the movement is horizontal. So, the fins invariably will be moving like this, so that they cool better. In contrast, the ones you see normally heat sinks and all, now we expect to keep them here. Now, these days it is fashionable, or rather fashionable, the thing which is coming back is so called 3D printing, and all of you must have seen the small devices which you build or buy at home. Better known of it as MakerBot. Next time you see the print head of the MakerBot, fins there are horizontal. Though it moves slowly, for various reasons they have put it horizontal. One of the advantages, in one end probably you can put a cooler or a fan, maybe put another suction one, and all the time we have a forced convection which helps us like that. So, the important thing whenever you are talking about anything including natural convection or free convection is the orientation of the fins. In the case of forced convection, we have a fan or pump forcing the coolant media into motion, which is normally forced. Advantage of is you have some control about it. Disadvantage of it is lot of power is involved, and for some reason if the pump or fan fails, we are in deep soup. So, you end up with other hardware. One of the hardware is something to sense the temperature. While you can build it directly into the chips or anything, you still need to see, to prevent damage, the rate at which things rise, you probably need something which has a flow sensor. So, you may end up with a small anemometer, or you may end up with Curie sensors, which see in the case the airflow falls some reason, there may be a blockade of the filters and so on, you need to take preventive action. One of the simple thing is try to reduce the operation of the devices, so that you can save power. And now with the intelligent things and possible, it is very much possible for you to make things much easier. So, you have got it. The advantage of natural convection is there no extra hardware involved, and it is slow, and then things equalize. As things equalize, they will do, there is no chance of failure. Even in case you have a filter, the catastrophic failure chances, rate of rise of heat is small. And in the case of forced convection, we have the disadvantage, thus in case of failure of one component in the forcing system, everything freezes, and unless you take upfront action, you may have problem. So, coming back, Basic relationship of convection from a hot object to a fluid presumes a linear dependence on the temperature rise along the surface of solid as Newtonian cooling. Therefore, we have total quantity of heat in convection as an area temperature different between the two, the medium and the source, into a heat transfer coefficient in convection. The beauty here is convective heat flow rate from the surface inwards, because it has been made very convenient, surface area for heat transfer, surface temperature, coolant media, coefficient of convective heat transfer. Here we have to face reality. Without theory, you cannot predict, or you cannot, without understanding the mechanism, there is no way for predicting the heat transfer coefficient in convection. And then without making an experiment, that theory may not have started. So, both go hand in hand together. You start with the experiment, set up a, make a setup, and then later on see how well you can make things. So, just now my colleague told me, hey, you have a trick question, why don't you show them the trick question. Next time when you have a chance, take any heat sink, take a large heat sink like this, no? Take this ugly monster, or you take this cute, I do not know, I will call it a cutie pie. One thing you notice is when you have fins here, you also have some small horizontal lines. Hey, it gives like a school bell. And now you would have guessed what it is. The main thing what it does is how to increase the area of interaction with the ambient. You will have them in all these things, how to increase the effective surface area. One way is try to calculate all these areas. Another is if you take a simple, a device like this and try it out, directly you can make a new heat transfer coefficient in convection with the given rates on this thing, and then if you just take the area, you will be able to get it. I expect they are all car enthusiasts. The moment you are a car enthusiast too, you will end up with CD, drag coefficient. So, they say given a surface area, this you can predict the drag coefficient. So, I am not very sure of the numbers. I expect that 0.6, 0.7, 1, 1.1 and all are very much in demand, and then I think you read it up. It's a little like that. Next slide comes to the most important part, the conduction. Is a transfer of heat from an area of high energy to an area of lower relative energy. You have seen this here, no? Heat is not treated as a fluid that passes through, because there is no passing there. In a heated mass transfer, we have a fluid in there. Here it is only energy in transition. So, something with a high energy to lower energy in transition is what makes. Conduction occurs by the energy of motion between molecules, by the movement of free electrons, and so on, so on. In the convective mode of heat transfer, we have no appreciable displacement of the molecules. So, he is being a little more precise, saying there is no appreciable this thing. The reality is there is no measurable unless you go to a very special thing. As it is, a solid remains a solid, and it is vibration of the lattice structure within the vibration. So, we need not. In the convective mode of heat transfer, we use conduction to draw heat away from a device, so that the convection cool the conductive surface, which is an air cooled heat sink. After a long time now, we are slowly coming into this, saying heat sinks invariably have to be cooled by another medium. So, by definition, it is just a heat spreader. It is not infinitely, it will not sink the heat. If you insulate it, which one of the experiments I have made a box there, and then I will show you. I do not know whether you are familiar with this one is a small heater from a This is taken heater from a mosquito what do you call pad. On the box it is marked as 230 volts into 7 watts. Okay. And then elaborate arrangements have been made to clamp it. I have clamped something on top, something at the bottom, and then you can see this here. There is a small ceramic thing. It is actually nothing but a thermistor with two what do you call rates of that temperature coefficient. There are two slopes like this. With this, it has a self-regulating property. As things heat up, it will start, it will allow large current to flow. When the temperature is below a certain what do you call set temperature limit, it allows a large current to flow. Once the temperature has reached that maybe 60 or 70 degrees, it will sort of reduce the heat flow and maintain it at that. I just wanted to show, I have mounted it on an aluminum plate and put it in a what do you call polystyrene PS foam expanded EPS foam box to show you that this whole plate will reach a temperature of 52 degrees centigrade, which normally if you keep this small thing in the air it will not reach. Two things, heat loss, second thing is the conduction. But you see here the main thing, the whole thing here is to make it by conduction, and there are no fins and all attached to it, because I wanted to make a hot plate which can be used for other purposes. One of them is, I mean, you can keep tea hot. I think you have seen the USB tea cup holders. If you keep hot tea in that, it will not cool down, because the temperature is maintained at about the what you call temperature I was telling you. You can put an insulator all around. In fact, you can put the whole USB cup heater into a box, leave it there for maybe half an hour or so, if possible with a kitchen thermometer, and notice that the temperature does rise, but if you keep it outside, it does not rise much, and in fact, unless you close it, you will not find it. There conduction plays a large thing, and then the moment you insulate it, it behaves. In the case of a heat sink, we will come back to this saying, we use conduction to draw heat away from a device so that the convection can cool the surface. I have shown you earlier a drive taken from a DC motor drive. There it has a PWM control. In spite of it, the mounting plate gets hot, and then they have given a provision such that we can mount it outside on a heat sink and then have all the power drawn out. For a one dimensional system, the following relation governs conductive heat transfer, which I have already told you about it. Heat flow rate in watts is proportional to temperature divided by all these things. And I will get back to this what do you call minus K at that later on. Cross sectional area of heat transfer, temperature differential, length of heat transfer. Since heat transfer by conduction is proportional to a material thermal conductivity, temperature gradient, cross sectional area, we can find the temperature rise and application by this. Okay. So, while that is a what do you call this thing, the whole thing has been reduced, and now I will get back to the thing saying that minus is not what it is supposed to be. Okay, it was just shown as a proportionality thing. So, we have this problem of, if we want to know the temperature difference, we need to have the geometrical parameters of it. Okay. Finally, we come to what you call the radiation. You will notice here that so far what we have talked about are two things real. I will see if I can go back to the